up to this point in our development of trigonometry, when we were dealing with triangles, the triangles were always right triangles. We can solve right triangles given a certain bit of information about right triangles. Well, we're going to extend our study now a little bit, and we're going to be able to solve oblique triangles, triangles that are not right triangles. And in that circumstance, though, we have a particular notation, and let's start with that notation. It's a notation we've seen before. It's the idea that the angles are labeled with uppercase letters. I have A, B, and C here for the labeling of the angles, and the sides opposite those angles have a correspondence in labeling. The angle A has the side opposite lowercase a. Angle B, lowercase b as the side opposite. Angle C, lowercase c as the side opposite. Now it turns out that there are actually two techniques that we're going to study here, but both of them involve the notion that we need this information in order to bring these ideas to bear on the triangle. We need the information about the length of one side, and we need two other parts involved in our triangle. Now the triangle has really 6 parts. There are 3 angles and there are 3 sides. So there are 6 pieces of the puzzle to be put together. Now if we have the length of one side and 2 other pieces of the puzzle, that is 3 pieces of the puzzle involving the length of one side, then we can solve that oblique triangle. Now, each of the 2 techniques we're going to talk about, one of them we'll talk about in this section, the other we'll talk about in the next section, but each of them involves a certain bit of information. We have to be able to identify the kind of information needed in order to bring the technique to bear upon that triangle. The first idea is called the law of sines, and it has to do with ratios of angles and sides opposite those angles. And it works like this: that side A corresponds to the sine of the angle opposite side A, you see, in the same way as side B corresponds to the sine of angle B, and this also would be equal to the ratio of side C to the sine of angle C. No wonder it's called the law of sines, you see, because we have sine all over the place here. Now, because we have the equality of a bunch of fractions here, we could use these in reciprocal form. That is, it's also true that sine A over A is equal to sine B over B is equal to sine C over C. Now, when we actually make use of the law of sines, we only use 2 of these angle side opposite pairs. That is, we involve A over sine A with B over sine B, or we involve B over sine B with C over sine C, or we involve A over sine A with C over sine C. You see, so it's this pair, that pair, or this pair in all cases. Now, and we could apply the same notion down here. But notice this, just conceptually here, that if we have just a couple of these pairs involved, that in this equation we have 4 pieces of information. Now we said earlier that we need 3 pieces of information, including the length of a side, in order to be able to solve the oblique angle. And just generally, when we have equations that have 4 variables in them, we need 3 of the 4 in order to solve for the 4th. And this just kind of meets with that general idea. Okay, now notice that if we have 3 pieces of information, and one of those pieces of information is the length of a side, and let's say it's the length of side B, all right, and we have 2 other bits of information. Look at what that information needs to include. It needs to include either the size of those other, of 2 of the angles, one of them being opposite B, or it needs to be one of the angles and another side. And there has to be an angle side opposite pair involved in the situation. Let me illustrate it like this. Suppose we have this triangle and we have the information that's given here. Now notice that we have B is 7, angle A is 60 degrees, side C is 10. Now we seem to meet the criteria here for being able to solve this oblique triangle. And we meet the criteria because we have the length of a side and we have 2 other parts to the whole puzzle. Okay, but it turns out that we can't apply the law of sines in this circumstance because we don't have an angle side opposite pair. What we have is information about side B, but no information about angle B. We have angle A, but nothing about side A. We have side C, but nothing about angle C. Now, what this means is that we have some information about every one of these fractions, but we can't use all three of them at the same time. So the idea is that we have to have, in order to use the law of sines, we have to have one angle side opposite pair. That's the point of this little discussion. Now, once we have that, we apply the law of sines. Let's take an example. All right, we have, let's get the lay of the land here. We have side C is 20. This angle C is 120 degrees. Now I'm noticing that we have the length of one side, that's part of the criteria to use the law of sines, or the law of cosines, which will occur in the next section. And we have an angle side opposite pair, and that allows us to use the law of sines. Okay, so we have an angle side opposite pair, and now we have this other angle as 45 degrees. So away we go. Now, let's kind of get straight about where we're going with this. We're thinking about this as a given angle side opposite pair. We have this angle, and the side opposite that angle is involved in the same fraction. You see, those rascals are involved in the same fraction. So we're going to end up solving for B. You see, we're not dealing with A or angle A or side A at this point in the problem. All right, so we set it up like this. Now I'm looking for side B, so I'm going to write this as B over sine B, and I have information about C, angle C, and side C. Now I have to have the same sense in this fraction as I have in this one. That is, if I have the length of the side in the numerator here, I have to have the length of the side in the numerator over here. So I'm going to have C then over sine C. Now, filling in, let's see, I have B over sine of B, that's 45 degrees. And C is 20. And angle C is 120. And away I go with solving. Now, I set the problem up so that the unknown quantity was in the numerator of the first fraction. You get a little bit of mileage out of doing that algebraically, because when you go to solve this, all you have to do is multiply on both sides by this denominator, this sine of 45 degrees in this case. So we would have B equals, now when you multiply by sine 45 over here, these would go out. So you imagine sine 45 right here, they would cancel. And then sine 45 over here, you see, goes into the numerator as a factor of the numerator. So we would have 20 sine 45 degrees over sine 120. And now it's a matter of using the calculator, and we find B to be approximately 16.33 units, whatever the unit is for the lengths of sides. Okay, so that's the idea. Now, at this point, we go through and we can solve for angle A and side A. Now, the angle is really easy because, after all, we have information about two of the angles. We certainly should be able to figure out the third because the sum of the angles is 180. We could have actually attacked the problem that way to begin with. Now, so let's go ahead and solve for angle A. We know A plus B plus C is 180, B is 120, C is 45. So solving this for A, we find A to be 15 degrees. All right, now we want to go through and solve for side A. Now, let's shift back over here just for a minute and have a look. When you are solving for the various parts of an oblique triangle like this, it's wise to use the given information as much as possible in solving for something that you don't know. For example, we found B to have the value 16.33, but it's an approximation. And I wouldn't want to use the B sine B fraction in the calculation for either angle A or side A. You see, I want to use the given information about this angle and that side in that calculation. So when I set up to find A, now notice I'm structuring it as A over sine A and then C over sine C, using this fraction because this is the given information. All right, sometimes it's, well, it's your option, but it is possible to solve for what you're looking for before plugging in. And I'm just showing that technique here. I don't always do it this way, and I don't think there's any great advantage to it. There may be in some circumstances, but it is a technique that can be brought to bear here. So we have, let's see, multiplying on both sides by sine A, we would get A is equal to C sine A over sine C. And then plug in, C is 20, A is 15, and C is angle C is 120 degrees. And again, we use the calculator to find A to be approximately 5.98. And we have solved the triangle. Now consider this one. We have A is 60 degrees, angle A is 60 degrees, side A is 9, and side C is 10. Now we meet the criteria for using the law of sines here because we have the length of one side and we have two other bits of information, and we have an angle side opposite pair. We have an angle side opposite pair. So we use the law of sines on this problem. Okay, now we haven't drawn the triangle. We don't need a drawing of the triangle here to use the law of sines. We simply begin by thinking, well, let's see. We have information about this angle side opposite pair. We have we have side C, so we're going to find angle C. So I'll set it up with the sine of that angle in the numerator of the left side fraction, just to make things easier algebraically, and this is over C. This is set equal to the sine of 60 degrees over the side opposite that angle, which is 9. And now I've got, well, I'm jumping the gun here. I should have let me just write the letters in here. I'm so anxious to get into the calculation. Now let me go sine A over A. And now I'll fill in. Sine C over side C is 10 equals sine 60 over 9. By the way, that little mistake that I just made of plugging in as you go along, there's a strong tendency to do that because it's such a simple formula. But I think you ought to train yourself, as I should train myself a little better maybe, to write the formula down first and then plug into the formula. That's a lot safer to do than plugging in as you go, because then the tendency will become to try to make calculations as you go along. You see, and you'll find yourself trying to do a little too much in the problem. Okay, so we have then that sine C is equal to 10 sine 60 degrees over 9. And we have the sine of some angle is equal to this fraction. You see, and now we can approximate that value, but then what is the sine, what is C? You see, we don't want to know what sine C is, we want to know what C is. So C, it will turn out, is the arc sine of that value, whatever it is. You see, or the inverse sine of this. So I can say arc sine of that fraction for calculation purposes. And again, punching the calculator, we find that C is approximately 74 degrees. Okay, now, then we think, gee, we took arc sine of some value to give an angle. Now wait, let's think about that a second, because you know we have the sine of this, the sine of some angle is some value here. That value is, well, it looks like to me it's positive, but the angle, the sine of an angle having a positive value, that angle could fall in two quadrants. Gee, that angle could fall in the first or second quadrant. So, gee, if it's a 74 degree angle in the first quadrant, well, let's look at it here with on a coordinate plane. We could have a situation where, I think, well, let me do it this way. I think we're more accustomed to seeing it like this. And that angle of 74 degrees could be in the first quadrant like this. And now notice that I'm reverting back to a right triangle here for the purpose of analyzing the sine of an angle, all right? And although our triangle up there, I'm not drawing the triangle at hand up here, I'm drawing an angle within a right triangle in order to make the calculation for the sine of C. Okay, so that's the idea here. But at any rate, here's one little right triangle, and the sine of 74 degrees. It's that 74-degree angle that we're talking about over here. Okay, fine. But there's a 74-degree angle over here as a reference angle that will do the same thing. And the angle then associated with it is this angle. I'm wondering if it's possible that it's this angle that we're talking about. Well, a reference angle of 74 degrees approximately is what? Well, 180 minus 74 would be that other angle, and it turns out that that angle is about 106 degrees. So C could also be an angle of 106 degrees. How is that possible? We could have two possibilities here. Well, it turns out that this is a somewhat ambiguous kind of case. And we get that occasionally in using the law of sines. And here's how it can occur. We can understand it, I think, from a construction standpoint. We have angle A is given to be 60 degrees. We have side C is given to be 10. So these are kind of etched in concrete. And the side opposite angle A is 9. Now, that 9, though, could be constructed in a couple of ways. That is, that side length of 9 can join from B to this side in a couple of different ways. Let me show you how that's possible. All right, here's this is 10, so 9 will be a little less than that, and I've just made it this angle opening, or this opening of my my compass. But if I just make a mark right here, this could be 9 right there. See, right about here. But I could also have a 9 up here. You see, so the angle that I'm talking about could be this angle for the angle for C, or it could be, you see, that angle for C. Now, which one is it? Now, this one, if we're drawing it like this, then this would be 74 degrees. And if we're drawing it like this would be the one that's 106. Now, most of the time, it'll be clear from the nature of the problem that you're dealing with of which one you need to choose. So just by the conditions within the problem, you'll kind of know which way to go. But here, we certainly don't. We don't have any other conditions. This is not a regular word problem. If we were told, for example, that we have an obtuse triangle, that's a triangle that has one obtuse angle in it, then we know that we use this version. You see, that we use a 106-degree angle for C. Now, but we have two conditions here, two circumstances, and we have to deal with both of them. Now, we know that the given information is still in place. So we have C is 10, A is 60 degrees, and side A is 9. All right, so this is 9, that's 9. Now, and we have two circumstances for C, which gives us two circumstances for the length of side B, you see? And it gives us a couple of circumstances for the size of this angle. You see, if we have a 60-degree angle here and 106 here, then 180 minus 106 minus 60 would be that angle. And if we have 74 degrees up here, then 180 minus 60 minus 74 would give this angle for B. All right, so that's pretty easy to see. What about the length of the side, though? Side B, how do we deal with that? Well, if C is 74 degrees, now this would be the case where we're dealing with this triangle, all right, then B would be 46. All right, so this would be a 46-degree angle using the technique that I just talked about. And then side B would be found by, well, it would be, if we're looking for side B, we're going to use B over sine B equals given information A over sine A. So it's B equals, now I'm kind of skipping a step here in the interest of space down at the bottom of the board, but we have A times sine B in this numerator, and the A value is 9, and sine 46, you see the sine of B, sine 46, and sine A is sine 60 degrees, and we find B then to be 7.5. So B is 7.5, that means this side would be 7.5. All right, the other circumstance is one where C is 106 degrees, and then 180 minus the 106 minus 60 leaves 14 degrees for angle B, and that would be the small triangle right here. Now to find this side B, it's again B over sine B equals given information in this fraction. So we would have A times sine B in this numerator. The A value is 9. Sine 14 degrees over sine 60. We find B to be approximately 2.5. Here's another problem where we're given information similar to the previous one. It says we have the size of an angle, we have the length of the side opposite that angle, and we have another side. All right, so we might be led to believe that, gee, when we solve for the angle opposite that side, it might be two angles that we're solving for. Let's see what happens. Now, because we have this angle side opposite pair, we're looking for the angle associated with that side, so we're looking for angle C. So sine C over C is equal to sine A over A. And sine C then over given 10 is equal to the sine of 100 degrees over 125. Multiply by 10 on both sides and we get this fraction. Now when we find the value of the fraction, we want the sine of the angle, we want the angle whose sine is that fraction. And so we want inverse sine of whatever number appears here. We find the angle then to be 4.5 degrees. Now, if we're thinking the way that we did in the previous problem, that gee, the angles whose sine or some positive number over here could appear in the first or second quadrant. So this might be a reference angle for an angle in the second quadrant, and we find the angle by taking 180 minus this, so the other angle could be maybe 175.5 degrees, we might be thinking. However, if we just look at the nature of the problem that we're given here, we know that we have to throw this out because angle A is 100 degrees, an obtuse angle, and a triangle can't have but one obtuse angle involved in it. We can't have another angle that's obtuse. It would cause the sum of the angles to be greater than 180. So we have to throw that out, and we're dealing with only one triangle in this problem. Okay, let's look at the triangle. Now, if we had looked at the diagram of the problem, we might have been able to think our way through the idea that the angle C can't possibly be obtuse because there's only one way to draw this triangle. And by the way, when you start to think about, is there one way to draw the triangle or is there another way to draw the triangle? If you think about those things in the context of geometry, you get a lot of mileage out of your geometry. It turns out that the proofs that you used in geometry kind of correspond with information given in the problems that we have here. Information about that is given in your textbook, and I'm not going to belabor those kinds of points, but it is the case that you can't prove congruence of triangles when you're given the length of two sides and an angle. And that's the information that we're given up here. We have the size of one angle and we have the lengths of a couple of sides. And unless the angle is nested between the two sides, you can't prove congruence of triangles. So that's one of those. So that's the correspondence with geometry that allows us to gives us a tip-off as to whether or not we're going to have, or we might suspect that we have a funny situation occurring. Okay. Anyway, to find angle B, now we've just discovered that the angle at C is 4.5 degrees. So this is 4.5 degrees. And now to find B, we take 180 and subtract 100 and subtract 4.5. We do this to find B to be 75.5. So now this angle is 75.5 degrees. And away we go to find side B. Well, let's see, it's going to be B over sine B and then given information involving the A's. Okay, so it'll be side A over the sine of angle A. So it's B over sine B, A over sine A. And so we have, let's see, sine of B we found to be 75.5, A 125. Sine of angle A is a sine of 100 degrees. Multiplying by 75.5 on both sides, we get this. And we find B then to be 122.9 approximately. Here's another problem in which something kind of funny is going to happen, but let's just understand that we are not going to recognize funny situations before they occur. A lot of times we have to sort of bump into them. And here's how we bump into this one. We see an angle side opposite pair, and we see some information about another side. And this is the circumstance where we know we can use the law of sines because of the angle side opposite pair. We might suspect that something funny can happen because we have the length of another side and not the size of another angle. You see, it's this circumstance that leads us to the possibility that something funny might be up here. Well, let's see. We have the length of side B, so we're going to solve for angle B. So it's sine B over B, sine A over A, the given information. And now B we know to be 12.8. Angle A is 58 degrees, side A is 4.5. All right, now multiplying by 12.8 on both sides, we get this fraction. And now, the sine of some angle is this fraction. And if you punch it into your calculator, you want inverse sine of this fraction. And when you do that on the calculator gives you an error message. It says, we can't do this. Now, why can't we do that? Well, it turns out that this fraction has a value of greater than 2. And we know that the sine of angles is a number that's between -1 and 1. And that's why the calculator is giving an error message. Now, why is this occurring? Why do we get a value of the fraction that is larger than 1 here? Well, it turns out just from the structure of the information that's given. Let's try to construct the triangle. Now we have this angle A and side A that's given. So angle A is 58 degrees. The side A opposite that angle is 4.5. We're also given that side B is 12.8. So we have a relatively long side here and a relatively short side opposite this angle of 58 degrees. Now, you see, the dilemma is that no matter how we sort of swing this segment of 4.5 right here, no matter how we structure it with changing the angle here, we can't make this side reach this opposite side. You see, we can't reach side C here with that side. Now, if we had an angle here that was a little bit smaller, you see, if the angle came down a little bit to where this rascal would touch down here, then we'd be okay. But it's just by the structure of what's going on with our lengths of sides and the size of this angle that it's an impossibility. So we're seeing a number of possibilities here for our problems involving the law of sines. We can be dealing with one triangle, we can be dealing with two triangles, or we can be dealing with no triangle at all.